Hello, good evening. Today we are having open session with week 9.
Good evening, ma'am.
Um,
Good evening, ma'am.
Yeah, good evening. So till now, we have seen random variables, distributions, and based on that, we found out this PDF, CDF, and all this stuff, right? And functions of random variable and all these things we have studied till now. So now, also we introduced sample mean, right? What does it mean by sample means?
Yes, ma'am. The sum of a sample, the sum of values in a sample divided by the number of objects in sample.
Yeah. When xi's are given to us, at that time, what we do, uh, let's say xi's are given to us, x1, x2, x3 till xn are some random variables given to us, which are IID samples such that they are following the distributions similar to, let's say, exponential random variable with some parameter lambda, right? We used to have this kind of information and we find what's the mean, what is sample mean, and related stuff, right? What will be the expected value of sample mean, variance of sample mean, and all these things. Here, one thing was known to us that these xi's are IIDs and they are following exponential distribution with some parameter lambda. Now onwards, our target will be to find the estimate for this parameter lambda. That means, for example, we have given the information that xi's are IID samples and they are following some distribution similar to, let's say, exponential distribution with some parameter lambda. But we are not given with this value of lambda. Like, then we will be interested in finding out what would be our lambda. That's what we call it as estimation of a parameter. Okay. So, for example, if xi's are following Bernoulli distribution, then what will be your parameter? Anyone? Let's say xi's are following Bernoulli distribution. Okay. Then what will become our parameter here?
Probability
P.
of success.
P.
Probability of success. Fine. Then you will ask, okay, we always know what is the probability of success. Then how will find out the estimate of parameter P, right? So is it possible that you always know what is the value of P for your particular experiment? Let's say there is some experiment happened and you have some sampling. Let's say uh, you have this kind of outputs 1 0 0 1 0 0 0 3 4 5 6 7 and this kind of information you have. Then how will you find what is your parameter P is taking here? Like what's the probability there? This is sampling one. For the first time, someone has executed experiment and he or she got this type of values for your x1 to x10 values, right? On the basis of this information, can we predict what is the value for P here? Yeah. What?
4/10.
4 by 10. So how did you find out that? You just calculated how many successes are there out of the given sampling, right?
Yes, ma'am.
Okay. Yes, ma'am. What if this was sampling one? That means someone has done executed the experiment for the first time. Let's say that the same person on next day came to the lab and executed again the same experiment, and he or she got this kind of information: 0, 0, 0. Let's say that 0, 0, 1, 1, 1. Then what will you say? Okay, this is 11 times.
6 by 10.
Okay. No, this is 1 by 2. That was 11 quantities. So here you are saying it's 5 by 10.
5 by 10.
Here you are saying it's 4 by 10. But this was the same experiment. Then why your values for P are changing here? So when we say Xi's are following Bernoulli random variable with the parameter P, then this P should be unique for all, right? Even though on a particular execution, your these values may change, then you will find out how far it is. This 4 by 10 is how far it is from your actual probability, right? Then if you know that here in this case, in the sampling 1, let's say this is your P1 value, let's say this is your P2 value, then you will check like which experiment was more correct to your given distribution, right?
Yes, ma'am.
But now onwards we will deal this kind of questions where this P will be unknown to us, this parameter will be unknown to us, and we will estimate for it, like how to check what might be your estimation for this parameter P. Okay. So there are mainly two methods. Method of moments, and another one is maximum likelihood. Okay.
ML.
Yeah, I know. Method of moment estimators, and this one is these are also estimators, maximum likelihood estimators. Fine. So we'll learn
Yes,
one
ma'am.
by one. Once you find out the estimator, then obviously, let's say for example, you find out the estimator for the Bernoulli random variable. That means you found out the estimation for P, right? Now we know that this P is what probability of success. Fine. Then the question will arise: how accurate or how biased, like we just say it, accurate, how accurate your estimation is, right? This we are finding the estimation for this probability for this P parameter P. Let's say you got some estimation. Let's say I'm just saying it as a P hat. Okay. Generally, we denote estimation like this, P hat. So now question will arise: how accurate this estimation is P hat for this P is. For that, there is a term, there is a concept through which we check whether your estimation is biased or unbiased. In statistical language, we say it as a biasedness. So we check for that whether your estimation is biased or not. So, do you have any idea, like whatever we studied till now? Can you just guess what quantity will check whether your estimation P hat is biased or not?
Movement.
Moment, but which one?
First movement.
First moment. That is nothing but the expected values,
Expectation.
right? Expected values.
Yes,
So,
ma'am.
if we check expected value of what P hat,
P
that
hat. Yes.
should be equal to what?
Then how a first moment will help us check?
Huh. So, what expected value gives us? If we expected value of if x is a random variable, then we find expected value of x,
Mean.
right?
Mean, ma'am.
Yeah.
Okay, mean for the
Most
distribution,
probable value.
most probable value, right?
Yeah.
That is what, if you do experiment on a random basis, then you will just predict your expected value, that okay, this might be the expected whatever the experiment is. If you know the distribution, if you know the PDF or PMF of the particular experiment, then whenever you will perform an experiment, you always have the expected values. That's what the most probable outcome. So that's why
Yes.
when we check this, we look for the expected value of our estimator. So what should be our expected value of p hat, so that it will become unbiased estimator for p? Any idea?
Ma'am, can you please repeat the question?
What might be the values of expected values of p hat, so that it will become a unbiased estimator of p? So
Zero.
let me just clear one thing. When we are checking biasness and you are finding estimation for p hat, what will be your target? Your p hat should be biased or unbiased?
Unbiased.
Unbiased, right? Once it's unbiased, then the outcomes, then the whatever the findings, that will be more reliable, right? So expectation of p hat, if it comes to be equal to p, then we say that estimation is unbiased. Okay,
Yes, ma'am.
unbiased. Then we say p hat is unbiased estimator.
Ma'am, here p hat is here
Parameter.
para-
Estimator, sorry.
estimated parameter.
Yeah,
Yes,
estimation
yes.
of p. Yeah,
Okay, ma'am.
yes. So just in case whenever we are checking biasedness or calculating the biasedness of any parameter, then we just calculate expectation of p hat minus p. That will give you the biasedness of what? P hat and p. Fine.
P hat.
Okay. So this was, but and just an observation, what this
Ma'am,
quantity will represent p hat minus p? Any idea? This is estimation, this is actual value, then we subtract
actual
actual
value.
value from the estimation, then what?
Error, ma'am.
It's
Error.
error, right? This is a error term. So also we can say it as a expected value of errors. Right? Okay, yeah. What was your question?
No, ma'am, got it.
Okay. So whenever we do the estimation, our next step will be like, okay, just check whether it's a unbiased estimator or biased estimator. Okay, so that we'll get clarification, we are getting the correct values or not. Fine. So you know one thing, right? That x1, let's say x1 to xn are following Bernoulli distribution. I'm just taking this example because it is easy to understand. After some clarification, we will move to some another distributions. Okay, with p, and it is also given that these are IID samples. Then there might be many estimators. Like, let's say some person one has found that this p is nothing but 1/3. Okay, this is one estimation, or generally they say it as a 1/2, like
Ma'am,
yeah.
ma'am, number of parameter is equal to number of estimator, na?
No, it's not like that. For the, see here, how many parameters are there in this particular question?
1.
1. But
No.
for the same one parameter, we can have many estimators. Like P is probability here, right? Probability of success. So someone will say,
Yes.
okay, if there are two options, one is success, one is failure, then obviously probability of success is 1/2. So this is some, what we say, guess estimate or just an estimator, right? This is also an estimation, right? And someone will say, okay, no, estimation could be like average of first two terms and then add the last term. This might be the estimator, right? This may become the estimator. Estimation is what? Whatever you guess that is going to help you to predict the values of your parameter. That is estimation, right? And someone will say, okay, probability of success, nothing but the average of whatever the outcomes are there. Let's say P3 cap is equal to, or weighted average, let's say twice x1 plus thrice x2 and just 5x 10 divided by 10, something like that. This might be the estimation. Then in that case, we will be like interested in which estimator is
Can it be anything algebraic or numeric?
what? Please repeat your question.
Can estimation be anything algebraic or discrete or anything like that? Function,
Generally,
equation.
see, for what values we are finding the estimators that are nothing but the parameter of our distribution, right?
Yeah.
So it will be more or less the combination of our random variables.
Okay.
So now when we have this many estimators, then which estimator will be best estimator? That will be a new question, right? So how to solve that question? So for that, we will use this Bayes rules. Whenever we find any estimator, then our first target will be just check whether it's a biased estimator or unbiased estimator, right? So we will just check, okay, expected value of P hat minus P, whether it's equal to 0 or not. If it is 0, that implies P hat is a unbiased estimator, right? So just tell me one
Yeah.
thing. Yeah. Also question.
No, ma'am, nothing.
Okay. And if it is a non-zero value, then we'll say, okay, it's a biased estimator. And what will be the bias? That number will be there. And from that number, we will predict something else, that is later part.
I have a question here, ma'am.
Yeah.
Here P hat is our estimator, and P is the parameter of the distribution which is unknown.
Yes.
What will it be given?
Mm-hmm.
For subtraction, expectation of P hat minus P, where we will have the value of P.
Sorry, where we have it?
I mean to say, ma'am, expectation of P hat minus P is equal to 0. And
Yeah.
where P hat is our estimator,
Mm-hmm.
where we will have the value of P given or not.
See, if you are checking the biasness, then obviously you need this value of P, right? But generally, we do not have the value of P. That's why we are seeking for the estimation, right? Otherwise, there is no need for this estimation. See, if you know the value of P, then what's the need of P1 hat, P2 hat, P3 hat? No need, right?
Yes, ma'am.
So generally, I'm just introducing one concept. That's it. Whenever this value will go to 0, that means you can claim that it's an unbiased estimate. Now, to check out of this three estimator, which will be your best estimator? Obviously, this P is unknown to you. If it is known to you, you will check. Okay, it's unbiased or not, and then you will decide.
If
But-
P is given, we can directly not we can directly check it is near to P or equal P hat or equal to P hat, then it is unbiased.
Yeah. So more or less similar answer. So if you have three values, let's say P1 hat, P2 hat, and P3 hat, then to check which one is the best estimator, we will just find one thing. What? We just discussed, right? Error P hat minus P is representing error, right? So I will find, because we know some inequalities, right? Chebyshev inequality, Markov inequality, all these things. Using all that thing, I will just first fix my bound for the error. That means delta. Let's say I bounded P by 100. I do not want my error to exceed this P by 100, right?
Yes.
So I will calculate probability that the my value of error is let's say is less than P by 100. So I will just calculate. I will fix this error bound, right? Error tolerance, we say. My error should be less than this one. And then I will get some probabilities, right? For this P1 hat, P2 hat, and P3 hat. Fine.
Yes,
Can we
ma'am.
sort out this? We have some methods to calculate this kind of stuffs, right?
Yeah, ma'am.
So by using that, whichever like P1 hat, P2 hat, or P3 hat, whichever estimator will give me the highest probability that this error is bounded by this what we say delta, then that will be my preference, right? Isn't it? I want my
Yes.
error to be less. So in such a way, we sort out which estimator is the best estimator for me. So that was one thing.
फोन खुद जा रहा था
Please keep your mic on mute if you are not speaking. So this is how we use our biasedness and error kind of stuffs to sort out this kind of stuff. Now, the next question, which is actually the most important question, how to find these estimations. So let's learn that. That is, first we will start with the method of moments. Okay.
Ma'am, I have a doubt.
Yeah.
Ma'am, do we get all this formula in the interim exam?
Formula like I didn't get your question.
In the first question, in the form of resources.
Formula
Okay.
for
In the
week
form of,
9 to 12.
sorry, where?
Formula in the week 9 to 12 means in the week 9, so many formulas there for the bias, risk.
So actually, there are not that much difficult. Once you learn the concept, the formulas are not big deal. I'm not sure whether it is provided to you or not,
Okay.
but I don't think so. It will be provided because these are some important thing that we have to learn as a, because we will be as an analyst or data scientist kind of stuff, right? Kind of course. So these are some needed things. So let's start with the method of moment. So what do you mean by this moments as initially discussed? How do we calculate moments of any random variable, that x is a random variable which is following some distribution? Then can we have its moments, like how many moments we can find out other stuff, anything? So expected value of x is what? First moment of the x. Expected value of x is the second moment, and so on. Fine.
Yes, ma'am.
So these are moment of a random variable x. So let's say x is having some distribution fx. Fine. And obviously, if it has a distribution, then there will be a parameter, right? Like, have you seen any distribution which do not have any parameter? Let's say
No,
x
ma'am.
is
No,
following
ma'am.
exponential distribution
No,
with
ma'am.
parameter lambda, right? So in this distribution, you know that once you know the value of lambda, you know everything about x, right? You can
Yeah,
give
ma'am.
me a exact value, exact PDF or CDF values. Once you know this lambda, that means this parameter has its own properties, right? That will determine the behavior of x and exact values of x, fine? So let's say there are some n random variables which are following the distribution as like exponential distribution with parameter lambda. Okay, xi's are IID samples. Okay, and they are following this one. Then the question will be find the method of moment estimator for lambda. Okay, then find
All the moments
estimation.
are the first moment.
Sorry, what?
All the moments are we need the first moment.
All the moments are first one. I didn't get what.
You can proceed, ma'am.
So the question is estimation of lambda. So there is one thing to note when you start with the method of moments. Just confirm from your distribution that how many parameters are there. So in this particular question, when we are dealing with the exponential distribution of lambda, how many parameters do we have? Only one parameter, right?
Yes, ma'am.
Generally, we denote moments by capital M. Okay. Generally, the moments are defined as or denoted as capital M. It's a function of x1 to xn, all the random variables. And it is, so as we discussed, like there will be a first moment, second moment, third moment, and so on. So your any kth moment is given by 1 by n summation of xi raised to the power k. Okay, I1 to n. So if I ask you from this expression, what will be your second moment? Then you have this information, right? And I am asking you, what will be the expectation of x square? Can you give me the quick answer for that?
Ma'am, 1 by n sigma x I square. Yeah, 1 by 2 sigma x I square. X1 square plus x2.
Xi square, right? I is equal to
Yes.
1 to n. Why we say that? Because this is generally the formula for moments, and this is nothing but the second moment for x. Fine. So in method of moments, there is one thing to note down. That is what? How number of parameters are there? How many number of parameters are needed to calculate to find out? Okay. So here only one parameter is there, that is lambda. So the procedure is like find the method of moments, okay, like sample moments. How will you find out that? So there is only one parameter, we will find one sample, one moment, and we will be dealing with the sample moment because we do not know the exact values, right? So let's say the quantities are there, okay. So one parameter, that means we need only one moment at this time. That will be m1 will be what? Expectation of x, right? And that is nothing but 1 by n summation I is equal to 1 to n xi's, right? So this is your m1. That just mark it as equation 1. And what we are interested to find out, the parameter lambda, right? Okay. So as our distribution is what? Exponential distribution. So just calculate as x is following exponential distribution with parameter lambda, then find expectation for x. We have calculated method of moment in general, expectation of x, right? Now find out the this was we called as a distribution moment. This was sample moment. Okay, so distribution moment will be what? If you know your x is a random variable which is following an exponential distribution, what will be your expected value of x?
Mean.
Yeah,
One by lambda.
1 by lambda. So this is another value you know, right? So this is equation number 2. Now our task, now we have, just observe that we have two means. This is sample mean, this is distribution mean, right? And if you remember, what was the formula for expected value of sample mean was equal to distribution mean? Do you remember that theorem? If xi is our random variable, IIDs, then we have calculated expected value of sample mean, which is equal to a distribution mean.
Yes, ma'am.
Right? So from there, we our next step will be to equate expectation of x, that means distribution moment, with m1. Okay. Using that, we'll just put all these values. So expectation of x, that is distribution moment, is nothing but 1 by lambda. And what is the value of m1 there? 1 by n. Actually, it is x1 plus x2 and so on, right? Divided by n. So from this, can we find out what are the values for, what is the estimation for lambda? So yes. So from this information, our lambda is what? N upon x1 plus x2 plus xn. See, in this step, we just write it as a lambda hat. Why? Because it's our estimation that if your x is following some random distribution which is equivalent to exponential lambda, that lambda exact value of this thing we do not know. That's why we are predicting, and our prediction says that, sorry, estimating, and our estimation says that this lambda hat might be equal to n upon this sampling, sum of all these values, random variables. Okay, are you getting my point?
Yeah, ma'am. But one thing, you said that estimation can be more than one. From here, lambda hat is equal to only one estimation.
Yeah, why it is so? Because we followed one method, that is method of moment. Okay. Now, in the next step, we will check what is the maximum likelihood estimator. See, I said there might be more than one estimations for a same parameter, for a single parameter. But if you follow one method, then obviously you will end up with the one estimation, right? So we started with the method of moments, and we got one estimator, that is lambda hat is equal to n upon x1 plus x2 till xn. Okay. So based on this information, there will be like questions will be, let's take one example. It is given that some xi's are random variable, IIDs are random variable, obviously. And they are, yes.
How this lambda converted to lambda hat? I did not understand.
Okay. It's just to indicate that this is our estimation. That's why I put there lambda hat. There's nothing. That's just a representation, because when you work with the biasness at that time, you should not get confused with which is your actual lambda and which is your estimated lambda.
Because, ma'am, I'm confused because lambda is known, and we are calculating for unknown lambda hat.
No, where is lambda is not known here. Like, how do you know the actual value of lambda here? We are estimating the value, the parameter lambda itself. It's not known. So this lambda hit is just a representation to distinguish it from the actual lambda, because when you will deal with some expression where lambda will be there and this estimated lambda will be there, then you should be able to differentiate both of them, right? So that's why I put their hat on. That's it. Okay.
Okay.
Ma'am, sorry, ma'am. Sorry, ma'am.
Yeah.
One confusion. You are equating the expectation of the distribution equal to the moment, first moment.
First moment, yeah.
Ma'am, they will be the same, isn't it, ma'am?
Sorry, there will be.
They both will be the same, right? Now,
See,
EOX,
this 1 by lambda is our distribution moment. Why I am saying it is a distribution moment? Because I know that x is following a exponential distribution with parameter lambda. So obviously that x will have first moment, second moment, all this, right? And this method of moments procedure has defined its own moment that in general the sample moments will look like this. Okay. And
We
that's
can
obvious.
also conclude that this is equating the mean from different methods.
From different methods.
One is we get the mean from parameter, and one is the mean we get from sample mean method.
Yeah. You can say that, but that will work that will work only when you are dealing with the one parameter estimation. Okay. Once you come with the two parameter estimation, then you will equate your second moment with what we say, second moment of your M2 and second moment of your distribution. Okay.
Okay.
See how it came. For example, if you have some data only, let's say you have these values 15, 16, 1, 2, 3, 4, 9, this kind of stuff, okay. You don't know, just you know that you have information, these are the values of some experimental outcomes where every value is independent on what the previous value was taken, right? And in that case, if you want to find what is the mean value, then what you do?
We will use sum of all these by number
n,
of this.
right? So that's why it is called a sample mean. When you have a sample and do not know anything about the sample, then how do you calculate your mean? That is nothing but the sum of all the values divided by n, right? And in other terms, we say it as a moments. First moment, second moment, third moment, and all these have some particular formula. But with the same given values, if I tell you that these are the xi's, these are some random variables, and they are following some distribution, exponential distribution with parameter 2, then just give me what is the mean of these values. Then how will you proceed? Then you will say, okay, nu is equal to 1 by lambda, right?
Yeah.
And you will say it is nothing but 1 by 2, isn't it?
Yes.
So did you get the difference? If I hide this information, your answer will be take sum of all divided by total quantities, right?
Yes, ma'am.
But if I say behind the scene, it is following exponential distribution with some parameter lambda, okay? That might be any value. Once I give you that information, you will not sum all this and divide it. You will just use your direct method that, okay, it's exponential random variable. Then I know it's very easy to calculate mean. It's just a 1 by lambda, right? So by connecting these samplings with our distribution knowledge, we estimate the unknown things, the unknown parameters. That's what we are doing estimation here. Okay. So this is one of the methods. How it works, we are dealing with that. When you go deep down into this, you will get to know that, okay, why it's working particularly like that. Okay. So let's say there are XIs are IID random variables, and they are following Poisson distribution, let's say with parameter lambda, and the sampling is given to you, let's say 3, 9, 5, 15, 10, and 12. Then can you find what is the estimated value for lambda? Do you know how to calculate this? Find.
First, we will calculate the mean of sample, and then uh, it, match it with lambda.
Okay, just try it. Just try it and give me what value you are getting for this distribution.
We are getting the sample mean is 9.
Okay.
And
So
we
very
equate it.
first thing you need is a distribution of Poisson, right? Poisson distribution. Do you know that?
It is lambda. Its Poisson distribution mean is lambda.
Okay.
And we equate lambda is equal to mean of this sample.
Yeah, that's it. So using method of moments, your distribution will be your estimated for value for lambda will be
1/9.
Yeah. Okay. So how it proceeded? So first thing will be, okay, X is following Poisson distribution for lambda. That implies expected value of X is what? New, right?
Yes.
And mean is what? For Poisson distribution, it is nothing but lambda, right?
Lambda.
And what is your M1 here? It is summation of like 1 by n summation xi. I is equal to 1 to 9, right?
Yes.
According to whatever we have seen, that we equate our expectation of X with M1, right? And from there we get to know that, okay, lambda is nothing but summation of, okay, all the random variable upon number of random variables. So it is nothing but the mean, sample mean, right? So lambda hat here, we just say it is a lambda hat because it's a distribution. Just to distinguish it, there is no any purpose there. Okay. So you calculated it, right? Summation 1 by 9, and what are these values? 1, 2, 3, 4, 5, 6.
1 by 6.
1 by 6. You got the value as
54.
9, right?
Summation is 54.
Summation exercise. Okay. Okay, summation is 54. So it's a 54 by 6 and 9. Okay. So using this lambda head, can you see? So how will it work? Now your question might be, okay, so what is the need there if you know this kind of stuff? You know one sampling, and using one sampling, you are estimating the value of lambda, right? Now, you know, there might be one question ahead of it that, okay, find the probability that xi is equal to 1. Can you find out that value then? Obviously, you can find out, right?
Yes, ma'am.
Because to
Using
find
the
out
Poisson
this value, only one thing was missing, that is the value of lambda, right? and by
Yes.
estimating, you got the value of lambda, that okay, it's 9, and now you will put that value and you will get some approximated value for that probability that x is taking value 1. Okay.
Yes, ma'am.
So did you get to know that what's the use there for this
Yes, ma'am.
estimation kind of thing? Yeah. Yes.
Ma'am, one thing, we are saying that it is lambda cap because we don't know exactly what lambda is, and then can be some error in lambda we have got. That's why we are telling it lambda cap. Is it?
Yes. Yes. There might be some error. It may or may not be the unbiased estimation. That's why I'm just putting their head. You can have your own own things to just distinguish it from the original lambda. Okay.
Yes.
It's an estimation. That's why we are saying it's lambda hat. I'm using the word estimation again and again. For example, if you are watching a cricket, okay, there's a cricket match and it's a first inning and it's a 20-20, let's say 20 overs match, and let's say at 16th over there is some score. Let's say the score will be 135 runs and 4 wickets, and you are on the 16th over. Okay. The similar situation as yesterday, right? So 16th over. Now, can you just, you will estimate some run, right? Some run for the team that, okay, at the end, this team will make some 180 runs or similar to that, right?
Yeah.
Isn't it? So this is your estimation, but this may not be your exact value. So exact value might be 174 or 176, something right there. Okay. So
Okay.
you estimate something, so you cannot say that this is the final value. This is your estimation. Similarly, here we are estimating for the parameters. Fine.
Yeah.
So just to distinguish it from the original value, I am just denoting it with the hat. In maximum of the books, you will find this hat notation for the estimation signature. Okay, so what if you have a random variable xi's, which are IID again, and they are distributed normally with mean and variance. Then can you just use method of moments and give the estimation there? Will you try that? And
Yes,
the
ma'am, we
next and the very first question of mine here is, what are the parameters here for which quantity you are going to estimate?
For mean, mu,
for the
and for the sigma square.
Okay, for mean and sigma square. That means this is the example with 2 parameters, right?
Yeah.
Yes,
Mu
ma'am.
and sigma square. Okay. So, okay, just try it. First, equate your first method of moment with expected value of x, and equate second method of moments that you know, right? Okay. So using method of moments, what we will do? We will equate our first moment of x with m1 and second moment of x with m2. Right? What is our first moment expectation of x? That we know, right? X is a normally distributed random variable. Expectation of x square. So this is nothing but mu, right? And what is m1? Summation of all the random variables divided by n. So I'm just keeping it as a small m1. What is expectation of x square? So we know that
Sigma square.
yeah, variance of x is what? Expectation of x square minus expectation of x the whole square, right?
Yes, ma'am.
So that is nothing but expectation of x square is equal to sigma square plus mu square. Okay. So this is sigma square plus mu square, which is equal to m2. Fine.
Yes, ma'am.
So from here, now we have two equations and two parameters. But there is one thing that is directly visible. That is what? Estimator for mu. What is estimator for mu here? Mu hat is equal to m1 from equation 2. Right?
Yes, ma'am.
Then
Yes.
we are left with the estimator of sigma square.
Sigma
That
square.
second parameter. And what will be estimator for sigma square then?
M2 minus M1 square.
Yeah. So sigma hat square is equal to what? M2 minus M1 square. Oh, sorry. Yeah. Mu square, right?
But mu we don't know, na, ma'am. So we will.
We will use mu hat.
Yes, ma'am.
Okay. So this is nothing.
And where do we get the mu hat is equal to m1?
This equation number 1.
In equation number 1, mu is equal to m1 now. So how do we get mu hat?
I just told you, na, whenever it comes to estimation, we just change the symbol for our parameters. That is this hat sign.
Okay,
So
got
make
it.
it as, yeah. So generally, when there is a one parameter, it's easy to calculate using method of moments. So yeah, m1 is nothing but the summation of all the values divided by n, right? And what is m2 minus m1? So m2 is what? Summation xi squares divided by n, right? Minus what is m1 there? Summation xi by n the whole square. Okay, that's it. That was estimator for sigma square. Okay, so this is how, if there are more than one parameter, we do things like that. So do you know any random variable except this normal random variable which has more than one parameters?
Gamma, ma'am.
Gamma distribution. Okay, so let's calculate parameter estimation for gamma distribution. So xi's are following IID samples with gamma distribution with alpha and beta. Okay, so yeah, find the estimation for alpha and beta. What will it be? So our first task will be to equate expectation of x with m1. What is expectation of x here? If x is following gamma distribution, then expectation of x is
Alpha
nothing
plus
but
beta by 2.
Alpha by beta.
alpha by beta. It's
Alpha by beta.
Yes, yes,
which
please.
is equal to m1. Okay, and what is m1? Summation of all xi's divided by n. Okay, but we will just keep it like this. That is equation number 1. And what will be our expectation of x square? Will be m2, right? That is another step. What is expectation of x square?
It's alpha by beta
That
square
is again, we know that sigma
plus
square plus
alpha.
mu square is equal to m2. Yeah. So
Sigma
what
square is alpha square by beta square.
alpha square by beta square, and what is mu square again?
Alpha square
Just a
upon
minute.
beta square.
Just a
No,
minute.
ma'am.
Variance
Sigma
is
is alpha by beta square.
variance is alpha by beta square, and mu square is alpha square by beta square, which is equal to m. Now, two equation, two unknown. We can easily find out what are what we say estimations for alpha and beta. Can you? What
Yes,
is the
ma'am.
estimation for alpha and what is the estimation for beta? So, whenever we go to find out the estimation, I just said to make a make a difference, we'll just put hat on all these quantities so that we know that okay, these alpha beta are actual parameter, alpha hat beta hat are their estimators. Okay. So, what will be your alpha hat there? So if we solve equation 1
M1
and 2,
into
alpha will
beta hat.
yeah, what?
Alpha hat is equal to M1 into beta hat.
Okay. So from equation 1, I have this one. So using this value in equation 2, that will imply what? Alpha is equal to beta m. So plus beta square m1 square, right? Square is equal to m2. Okay. So this is nothing but beta hat is equal to m2 minus m1 square. Okay, that will be square upon m1, right? Is it?
Yes.
And
Yes, ma'am.
alpha hat will be equal to beta hat m1. That is equal to m1 square upon
M2 minus M1 square.
minus this is m1 square, right? Okay, that's it.
Ma'am,
Yeah.
could you please explain beta hat? How come it's m1 divided by m2 minus m2?
So it's nothing but the simplification of this equation, which is nothing but m1 by beta. Let's put height there. Plus m1 square, which is equal to m2. Once you simplify it, what will you do? Just subtract here and then.
But where is beta?
Huh?
Beta cap. There is no beta cap, right?
Beta cap is the estimation for beta. That's why I'm putting there cap instead of simply writing beta. From this, see, from this equation, you will find the value for beta, right? That will be like this. But this is nothing but, this is what? Estimation for the parameter beta, right?
Right.
So for estimation purpose, to indicate that this is estimation for beta, I am putting their head. This is not actual value of beta, this is estimation of beta using the method of Lorentz. Okay. Like in the initial example, when I say if your X is following Bernoulli distribution with parameter P, then I can have three estimation, P1, P2, P3. Okay. So I don't know which one is exactly matching my matching with my actual parameter P. So there I put P1 hat, P2 hat, P3 hat, just to inform that these are the estimators of P. Similarly, I found out the values and put their cap to just indicate that this is estimation. These are not actual values. Okay, fine. So after that, there is another method, that is maximum likelihood. Okay, that is another estimation. That is another method by which we estimate the quantities of parameters. We say it as a MLE, maximum likelihood parameter estimate. So here we will have some information that okay, xi's are following some distribution IID x, and where x will have some parameter, let's say parameters maybe let's say theta 1, theta 2, and so on, theta n. Okay, exponential we have started, so I think that would be the better example. Let's say xi is following exponential distribution with parameter lambda, and these are IID samples. Okay, then method of parameter says that once you know that your distribution is following that your random variable is following particular distribution, then just find out whatever what's your PDF there. So do you know what's the PDF of xi if it is following exponential distribution?
Lambda e to the power minus lambda x.
Okay. So what is parameter here? This lambda is parameter, and we are estimating for lambda again. Just remember, in method of moments, we got one value of lambda. Now here, let's see what the values we are getting. Generally, this is so there are n random variables, right? Our IID sample are n IID samples. Okay. So x1 to xn n random variables are there. So you have n random variables, fine. So just note one thing, in method of moments, what were you using there? Just check. You were using that moments formula that was generalized, that mk is equal to what? Summation of xi power k, right? Yeah. Moment formula, that is mk is nothing but the 1 by n, that is weighted average, summation of xi power k, right? That was your moment formula generalized, and you were using the then moments of your distribution. If it is a exponential distribution, you were calculating first moment of the exponential distribution, equating it with the sample moment, right? Here we will use something different. We will find first likelihood function. Now your question will be, what's the likelihood function? So if you have n random variable which are IID samples and following some distribution, then your likelihood function is denoted as L of x1 to xn, and also slash lambda. Why to denote? Just to denote that parameter is lambda here. Okay, for all this random variable, which is given as nothing but the product of all the PDFs of your distribution xi for lambda. Fine. Product of PDFs of all the random variables.
Ma'am, what is pi here?
Okay.
How do we use the pi?
Pi is nothing but the symbol to represent product. For example, we use summation sign, right? Which denotes
What's
whatever
summing?
inside it. It's just a we will sum it. Okay. That's what this represents, summation xi, right? Instead
Yes,
of
ma'am.
summation, if I want to write that product of xi, so I will write it as a, this is not pi, this is product symbol.
Okay, ma'am.
So this is xi, then this is nothing but x1 into x2 into till xn. Okay, this is product. How do we write pi? Something like this, and this is product. Fine. So just product all these PDFs, that's known as likelihood function. Okay, this is known as likelihood function, denoted as L of x1 to xn till lambda. Okay. So what will be the product here then if we know that Rx is following exponential distribution? This will be the product I is equal to 1 to n lambda e to the power minus lambda x, right?
Yes, ma'am.
It will be a xi. Then if we solve it further, then what will you get?
Lambda raised to the power n
Yeah,
into
lambda raised to the power n into e to the power minus lambda x1 into e to the power minus lambda x2 and so on, right? That is nothing but what?
Addition.
Addition. Yeah. E lambda power n into e to the power minus
Minus
lambda
lambda
common
x.
and x1 to xn, right?
Yes,
Okay,
ma'am.
that is what your L. I'm just simply writing here L, likelihood function. Remember the method's name? It was maximum likelihood function. Okay. Spelling mistake. Likelihood. Okay. So now this is one of the function. We will find the, we will maximize this quantity. How to maximize any quantity? Do you know that?
Ma'am, we will equate differentiation of that equal to 0.
Yeah. Differentiate, okay, but with respect to what?
A function x, if it is an
X, okay. So here then x1, x2, xn all are independent random variables, all are independent variables, right? So with
Yes.
respect to x1 or with respect to x2 or what? We want maximize value for which thing? Like our aim is to estimate the lambda. So we will maximize in terms of lambda. Okay. So whenever our target is to estimate in terms of lambda, we will differentiate with respect to lambda. Okay.
Okay.
Okay. So let's just differentiate the dl by d lambda and equate it to 0. That will give us a maximization of this function. Let's say equation number 1. And
So, ma'am, here
Mhm.
both are variables, lambda and x also.
Yes.
Okay.
Xi's are also random variable. Lambda is also not variable, but yeah, for
But because
as
we
of now
don't
it
know.
is.
Yeah.
As of now it is, because why it is lambda is a variable here, you know?
Because we
Because
don't know.
yeah, we don't know, and we are predicting this value of lambda using samplings. So once you vary the sampling, parameter will always change, right? For example, just remember method of moment estimator for this exponential distribution. See, we were using here method of moments. We estimated the value, this one, right? Now you change this xi value, your lambda hat will change, right?
Yes, ma'am.
Because every time you perform the experiment, these xi values will get changed. So using samples, you are predicting, you are estimating lambda, your parameter. That's why it's created as like that. Okay, just in this case, how will you do that? Now, to differentiate this equation with respect to lambda, what will you get here?
N into lambda to the power n minus 1.
N into lambda to the power n minus 1 into, we have to use a product rule, right?
Yes, ma'am.
And
And
still
this is the
there are
other
some
part.
terms like that. So it will be a very complicated things, right? So instead of that, I will use something similar to that, which will make this calculation easy and maximization easy. So can I use, like, is it okay if I find out if I maximize L and if I maximize log L, will they give me the same answer? Are they same? Maximization of L. L is the one, L is this function, right? And maximization of log L. Will they be same thing? Yes, they will be.
Yes,
Why?
ma'am. Differentiation of log x will be 1 upon x.
Is that the reason?
But it is differentiation of log L will not give us 0.
Why? The thing is, I will change my function, that is likelihood function, L, to log likelihood function. Is it fine? If I take log on both sides of equation 1.
Ma'am, how L and log L will be same? Maximizing L and log L will be same.
Yeah,
Yeah.
ma'am.
So, do you remember how this log function is?
It's increasing function.
Increasing function. Anything else?
It's monotonic.
It's monotonic. Anything else? Bijective? What is the domain for log function?
Positive
Positive
real
R.
numbers.
Yeah, positive real number. Fine.
Yes.
Yes.
And what is the range for it?
All the real numbers.
All the real numbers. So, okay. So it is bijective function. The main thing is bijective function. Once you, and what are the, like what say, the benefits of bijective function?
1 and on to both.
1 and on 2. So generally they say with maximization, why we take log? The reason behind that, the calculation that your product terms will get split into addition, right? And your powers will also come out. So
Yes,
your calculation will be easy. But why to do that? The reason behind that, it's a bijective. It's a 1 on 2. So you can map like that. That's somewhat discrete mathematics that I don't want to go inside. But yeah, that is one of the reasons. So for that purpose only, to simplify this equation, we will take log on both sides. Okay. And we will get log of L is equal to what will happen here? Lambda power n e to the power minus lambda plus xn, right? So yeah, this is product. First it will get split into addition, right? So
Yes.
log of lambda n, that will be n log lambda, right? Plus
Yes.
what will be minus lambda x1 to xn, right? Into log e. Is it so? And log e is what?
1.
1. If the base is e. So we just take e only, right? N log lambda minus lambda times x1 to xn. Fine. Now our task is to maximize this log function, log L. So how to maximize it? So we will just differentiate this with respect to lambda and equate it to 0. Okay. So once you differentiate this equation 2 and equate it to 0, we will get what? N by lambda. Differentiation of this with respect to lambda will be n by lambda minus this will be what?
x1 plus x2 plus
xn, which is equal to 0. Then from this, so again I will put hat here. Why? To just represent that now whatever we are getting in terms of lambda is nothing but the estimation of lambda, right? And lambda hat will be okay. Did you guys observe one more one thing? Estimation of lambda using maximum likelihood is similar to method of moments.
Yes.
Okay. Later on, we will also get to know that this is unbiased estimator. But for that to check that kind of stuffs, we need some more confirmation, like minimum variance and all these things. I don't think so that's a part of course, but if you are getting the same estimation using various methods, then there are higher chances. I'm saying chances, okay? It's not always true, right? This might be your unbiased distribution. Fine. But it may be possible that method finding the estimation using method of moments and MLE may differ from each other. Okay. So did you get how to calculate, how to find this maximum likelihood of any parameter? Any doubt there?
Ma'am, in different distribution,
Mhm.
we will do it like this, like log L.
Yes, exactly. I will just, once you guys are clear with this concept, then we will take some examples.
Please sum up once.
Yeah, where we take real values and find the estimation in terms of numbers. Yeah, summarizing is like that. Whenever we are using, whenever you are estimating using maximum likelihood estimation, at that time, first our task will be to create a likelihood function. Likelihood function is nothing but the product of PDF your distribution. Once you find the product of your PDF, we have to maximize this function, but maximization of product kind of thing will be difficult. So we will take log on the both sides so that this product will will convert into addition kind of thing, and problem will become easy. So just to convert this likelihood function into log likelihood function and find its maximum value in terms of your parameter. Find maximum, like maximize it in terms of your parameter. Here our parameter was lambda, so I differentiated it with respect to lambda and equated it to 0. Then I found out the values of lambda. Okay, is it fine? Let's take with one another distribution. Poisson distribution.
Ma'am, let's take a normal which have two parameters. Like in that.
Okay. Let's say we have n random variables and they are distributed normally.
1 minute, 1 by lambda should be equal to that.
What? 1 by lambda? Yeah. In case of Poisson, right?
No, previous one.
What? PDF? What? Can you please repeat?
N by lambda is equal to x1 plus x2 is equal to n. Then 1 by lambda is equal to x1 plus x2 by n.
Yeah, and then lambda bar should be opposite of this, n upon something.
Oh, yes. Thanks. It will be n upon x1. Yeah, correct. That's what you are saying, right? Yeah, sorry, that was my mistake. N upon summation of, correct. So that's our estimation for lambda hat. Okay, it was exponential, right? An exponential, okay. Fine. So normal distributed and using MLE, we are interested to find out the estimation for nu and sigma square, right? So for that, first we need is its PDF. What's the PDF for a normal distribution?
It's 1 by sigma root 2 pi.
And IID samples. Yeah. Just a minute. Yeah. Fx of x will be 1 by square root 2 pi.
Sigma.
Okay. Just take it sigma square because now our parameter will be sigma square. That will help you.
Yes.
E to the power
minus of x minus mu whole square.
The whole square divided by twice sigma square. Okay.
Yes.
Will you guys try it or what? So first step is form its likelihood function L. Right?
Yes.
It will be x1, x2 till xn for the parameters nu and sigma square. So just remember our parameters are nu and sigma square, not sigma. Okay. Just be careful with that.
So what will change, ma'am?
Nothing will change. You have to differentiate it first with respect to nu and later with respect to sigma square. With
First
respect
we
to
will
sigma
find it.
square, not sigma. Yeah. Yeah. So just product I is equal to 1 to n 1 upon square root of 2 pi sigma square e raised to the power minus x minus mu the whole square divided by 2 sigma square. Okay. Some constant terms is there.
Yes, ma'am.
Yeah, then
So we will outside it, like 1 by root 2 pi will come
Yeah.
outside.
just we can write 2 pi sigma square divided by n by 2. Is it fine?
Yes, ma'am.
Yes, ma'am.
Into this will be what? Expected e to the power 1 by 2 raised to the power and sigma square to the power. Okay. Minus 1 by 2 sigma square. These are common quantities, right?
Yes, ma'am.
Summation of what? Xi minus mu the whole square. Is it fine if I write like that?
Yes, ma'am.
Or you can just split it and then take addition. Okay, then what will be our next step? Take the log likelihood function. Once you take log, what will get? Minus n by 2.
It is with respect to mu.
With respect to mu, it's not differentiation. We are taking log only.
Yeah.
We are not doing anything else. So yeah, once you take log, what will be there? Raised to the power minus n by 2. So okay, 2 pi
Log 2 pi
sigma square, right?
Yes, ma'am.
And what will be here? Minus
1
by 2 sigma square summation I is equal to 1 to n xi minus mu square. Okay.
Yes.
This is what our equation. Now, our task is to differentiate this function with respect to nu and equate it to 0. But mathematically, now we are not maximizing it. Now we will minimize it. Why?
Why, ma'am?
Because this whole quantity is in negative term.
Okay.
So when function is in negative, like let's say, maximizing negative f of x is equivalent to minimizing f of x. So we will not deal with negative sign. We will instead do minimization. So nothing is
It
going
can
to
also
change.
be done in a way that -1 multiply this and -1 will go to through log L.
Yeah. That's more or same thing, but just I am just clarifying in mathematical. That's
Yes, ma'am. I understand.
okay. Even though you differentiate it with respect to nu or sigma square, your minus sign will get removed. That's not a problem. I'm just informing that we are doing minimization now. Or you can
Okay.
say that just remove this sign, no problem. Okay. So now we have to estimate for nu and sigma square both. So first we'll do with the differentiate with respect to nu. Okay. To just find out the estimation for nu. So del log L upon del nu is equal to 0. That implies what? This term will be 0, isn't it?
Yes, ma'am.
And here what we will have 1 by 2 sigma square. Here summation I is equal to 1 to n twice xi minus mu into minus 1, right? We are
Yes.
differentiating with respect to nu, which is equal to 0. That implies what? 1 by 2 sigma square. Okay, 2 can be outside. Summation xi minus mu I is equal to 1 to n, which is equal to 0, right? So this is the constant term, will sigma square will go to 0, and that's nothing but summation xi minus mu is equal to 0, isn't it?
Yes, ma'am.
Constant term will be out. Summation xi minus, this will be nu is a constant, so summation 1 to n is equal to 0, isn't it? So this term will be n nu, summation xi minus n nu, which is equal to 0. Okay, I should write here nu hat here. Why?
Yes, ma'am.
To just distinguish that this is estimated, not the exact value of nu. So from here we got that nu hat is nothing but summation of xi divided by n, right?
Yes, ma'am.
So remember, this is nothing but the sample mean. That's it, right? Xn divided by n. Okay, that's our estimation for nu hat. Fine. Now for sigma square. For sigma square, what we will do? We will differentiate log L with respect to sigma square and equate it to 0 to find out the estimation for sigma square. Fine.
Yes, ma'am.
Now just take it. So this will be n by 2, 1 upon 2 pi sigma square, right? As we are differentiating with respect to sigma square, so I will not write it as a twice sigma, right? Why? Because I am not differentiating it with respect to sigma, I am differentiating it with respect to sigma square.
Okay, ma'am.
Okay, that's why I told you here that to keep it sigma square instead of sigma. So then minus,
Yeah,
minus of 1 upon 2, it's a 1 upon 2 sigma square, right? So yeah, what will be its differentiation? 1 upon 2 into minus 1 upon 2 sigma square, right? S to the powers 2, isn't it? What is the differentiation for 1 upon x?
Ma'am, can you write down the equation here so that we can follow it?
Yeah, just I will just copy it. So we are doing del sigma square of what? So what? Minus n by 2 log of
2 pi
pi.
sigma square.
Just a minute. Yeah, del sigma square of, what was it? 1 by 2 sigma square or n by 2 something like minus n by 2.
Log of 2 pi sigma square minus 1 by 2 sigma
1
square.
by 2 sigma square. Okay, yeah, summation. Xi minus
Xi
mu
minus mu
whole
ka whole square.
I is 1 to n. Okay, this differentiating with respect to sigma square and equating it to 0. Okay, so yeah, for this term, minus n by 2 log of 2 pi sigma square with respect to sigma square. Just take, if you are getting confused with the sigma square, we can change it to, instead of sigma square, change it to y. Wherever we are finding sigma square, just change it to y, or just continue like that. So the constant here is n by 2, and what is the differentiation for log function? That is nothing but 1 upon x, right?
Yes.
2 pi sigma
Sigma
square. Minus here 1 upon 2.
Into
Okay.
2 pi or
What? Into 2 pi?
yeah, 2 pi sigma square.
Okay,
Then
okay,
we
yeah,
will,
yes. Nice. Okay, then 1 upon 2 constant sigma square. Now, how to do that? Okay, here one more thing will be there. 1 upon 2 sigma square. So, let me just expand this term. Is there anything that can be converted into sigma square? Okay, that will also play a role. Let me just expand this summation. Okay, we will just hold this equation here. Summation xi minus nu the whole square. That can be written as what? Summation of xi square minus twice xi nu plus nu square, right?
Yes, ma'am.
So okay, this is what summation of xi square. Okay, minus if we just get okay, twice nu summation of xi, right? And plus summation nu square. That is what? Summation xi square minus twice nu. Just remember, twice xi by nu is what?
Nu bar.
Summation xi upon n is what? Nu, right?
Yes, ma'am.
So we can write this as a n nu.
Yes, ma'am.
And this is what? Again, n nu square. Fine. And anything for summation xi square? Okay, just a minute. Hold. Summation xi square. Okay, just when we write sigma square is equal to what? Expectation of xi minus what? Expectation of xi square
Xi
minus
square.
Expectation of xi square minus expectation of x whole square.
sorry, yeah.
Whole
So
square.
anything for this summation xi square?
Yes, ma'am. Sigma square plus mu square.
That is what expectation of xi square, right?
Yes, ma'am.
Sigma square plus mu square. And this summation xi square is not like that, right? So, okay, but no need to do that, I think. Okay, it's not affecting our sigma square because the term, like my concern was, is this term going to be converted in terms of sigma square? So it is not going to. Why? Because this is summation of xi square, summation of xi square, right? And we are not in the method of moments direction. We are in the maximum likelihood function. So here, expectation of xi square is not going to be equal to 1 by n xi square, right? So we can take this term as a constant and solve it accordingly. There is no issue. Are you getting what was the concern?
Yes, ma'am.
Okay. So this term is not going to affect our calculation. So we will continue. We will just take all the constant term outside. That is this one also. Xi is equal to 1 to n xi minus nu the whole square into what was our we were doing differentiation with respect to sigma square of 1 upon sigma square. Yeah. Then what will be the next step? Yeah. Yes, what should be the next term? Differentiation of 1 upon sigma square. What is the differentiation? Yeah.
Minus 1 by sigma square.
Raised to the power 4, no?
Yes, ma'am. Sigma square whole square.
Yeah. So it is nothing but 2 pi will get cancelled here. And this is n by 2 sigma square minus this is 1 by 2 summation xi minus mu the whole square. And this is what? Negative 1 upon
sigma 4.
Sigma raised to power 4, which is equal to 0. Okay, this is totally different. Please don't mix them. Okay, this is outside the summation sign. Okay, then This is nothing but 1 by 2 summation xi minus mu the whole square. Let me just write it here. 1 upon sigma power 4. It is equal to n upon 2 sigma square, isn't it?
Yes, ma'am.
So yeah, just solve it. What will you get? The square power 4 get cancel, and sigma square is what? Summation xi minus mu the whole square divided by what? N. So that is our variance here. And again, one more thing. We are calculating sigma square head estimation. And this mean also we do not know. So that's why we will be using estimated mean. Okay. Estimated mean, you know what is estimated mean? That we calculated just before this. Okay. So this was all about how to get estimation for normal distribution. So just let's recap it. So x1, x2, xn are normally distributed IID samples. So here there are two parameters, mu and sigma square. So we have to differentiate it with respect to mu first and then with respect to sigma square. Okay. So we will just first create our likelihood function, which is nothing but the product of all the PDFs. That is product of all the normal random variables x1 to xn. Then to make it easy, we will take log function and maximize it with respect to mu first and then with respect to sigma square. Here, as all the quantities are in negative term, I am saying it's not a maximization. We are doing minimization, which is almost equal to do that. So with respect to first, we will differentiate it with respect to nu and find the estimation for nu. That we got to know that it's nothing but equal to sample mean. Then we differentiated the whole term with respect to sigma square and got to know that, okay, variance of this normal distribution is summation xi minus mu. Like it's just a sample variance, right? Even though if you don't know how to calculate variance of a normal distribution, if I give you some quantities, let's say some 10 quantities I am giving to you, and I ask you calculate its variance, what will you do? You will just directly use this formula, right? Isn't it?
Yes, ma'am.
We find the mean and use this formula, but here it came to be the estimation of normal distribution. But if you remember one theorem there, variance of sample mean is what was equal to?
Sigma square by n.
Okay, and there was one term we have learned that if Sn is something like summation of xi minus mu the whole square divided by n minus 1, then variance of Sn is equal to sigma square. Do you remember that?
Yes.
That we also have discussed in the solve with us session. So actually this one, when it is divided by n minus 1, that is actually the unbiased estimator for normal distribution, the variance of sigma square. And once we take this one, this quantity with actual variance, then this quantity will come out to be biased vectors.
I have a doubt, ma'am.
Yeah.
Can you explore it?
Yeah.
Explore a bit. Yes, ma'am. Here, how did we write minus 1 by sigma raised to the power 4?
Okay. If do you know the differentiation of 1 by x?
Minus 1 by x square.
Minus 1 by x square. Okay. Now in our question there is not x, there is sigma square. It will be what? Minus 1 by sigma square the whole square, right?
Yes, ma'am. Got it.
So it's a 1 by sigma power. Okay. So these were some concept that was covered in this week 9. Do you guys have any problem, any doubt in these concepts? Then just ask me, or we will do some questions here. Any doubt? What we learned today is how to check biased. Is your estimator is biased or not? That is biasness of your estimator. theta cap. Generally, theta is what estimation sign. That is what
Ma'am, you have
expectation.
missed the topic risk.
Yeah, risk is nothing but the like expectation of error square. Theta
Yes,
one.
ma'am.
Yeah, risk is nothing but the there is another one concept that says the risk. That is nothing but the expectation of theta cap minus theta square, right? Isn't it?
Yes,
So
ma'am.
that's one quantity which is useful to calculate squared error, also called as mean squared error. Why it is mean squared error? Kind of mean squared error. Okay. And method of moments
Yes, ma'am.
and maximum likelihood function. In method of moments, what we did, we equated our moments of distribution with sample moment and with sample moments. That's it, right? And in maximum likelihood function, what we did, we used PDF of our distribution, right? So that's what these was the main topics to in the week 9 that we covered today. In maximum likelihood function, we formed a likelihood function and then took the log of it to make for the simplification and maximized it by differentiating differentiating with respect to parameter to get the estimation of it. Yes, what was your question?
And when we will do the solve with session tomorrow?
Yes, it's tomorrow. And one more information is that on your portal, we have sent the Solve with Us session slides of week 9. So please go through it and check the questions. If you have doubts there, we will have session tomorrow and we'll discuss there. As due to quiz to your deadlines are very near, that's why we shared it with you on your portal. Okay.
Ma'am, the deadlines will be extended.
Yes, ma'am.
Not, most probably it will not. So Solve with Us session is tomorrow only. But I will suggest you to please go through that question once, and so that when we discuss tomorrow, it will be more easy.
Okay, ma'am.
Okay. So I hope you guys got these concepts, and
Yes,
we'll
ma'am.
solve the
Topics are clear. When we do some questions, it becomes strong.
yeah. So we will discuss questions and solve the questions tomorrow and solve some of them. Okay.
Okay, ma'am. Thank you, ma'am.
Yeah. Thanks.
Thank you, ma'am. Ma'am, quiz 2 exam was so easy.
Okay, that's good to see. Good to hear. Okay, so you did calculation all this perfectly, right?
Yes, ma'am. So many questions are from the class.
Oh, that's great.
Mock, ma'am.
Yeah.
Questions were from mock. Maximum questions were from mock test.
Similar to mock test, right?
Yes, similar.
Yes, ma'am. Mock and PYQs.
Okay. Okay. Thank you. See you later.
Thank you, ma'am.